If you ask anyone to name the most obvious truth about the world around us, they'll tell you the sky is blue. It is the literal backdrop of our lives. For centuries, that color was attributed to divine forces. That changed in 1665, when Isaac Newton used a simple glass prism to prove that white sunlight is actually a composite of 7 distinct colors traveling together in a single beam. Newton showed that each color operates at a different wavelength. But when we apply those measurements to the gas molecules in our atmosphere, the math points elsewhere. Based on the physics of light, the sky should be a brilliant violet. This means the image we see when we look at the horizon doesn't actually match the specific wavelengths of radiation flooding the atmosphere. To understand why our eyes perceive a blue sky when the physics suggests a different color, we have to look at what happens when sunlight is physically shattered long before it reaches the ground. In the vacuum of space, light travels undisturbed. With no particles to hit, those waves move straight past your line of sight, which is why the void between planets appears pitch black. But Earth is wrapped in a dense ocean of nitrogen and oxygen. When white sunlight hits these gases, it acts like a speeding truck. The light waves collide with the molecules, scattering in every direction. This isn't the same as light bouncing off large particles, like dust or water droplets. That process is called the Tyndall effect, and it can make a beam of light visible in a smoky room, but it isn't what colors the clear sky. The true mechanism is Rayleigh scattering. It only occurs in the upper atmosphere, where invisible gas molecules are spaced at least a full wavelength apart. At this scale, the microscopic size of the gas molecule determines how the light breaks. To see that process, we have to look at the molecules themselves. Light is an electromagnetic wave. When it strikes an oxygen or nitrogen molecule, it forces the electrons to wiggle. These molecules naturally resonate in the ultraviolet spectrum. Because blue and violet are closest to ultraviolet, the atmosphere scatters them 10 times more than red. This means the color of the sky is a direct physical measurement of how violently light waves interact with atmospheric matter. We see this every evening. When the sun is low, light travels a much longer horizontal path through the atmosphere to reach you. Over that distance, blue and violet are scattered away entirely, leaving only unscattered red and yellow to reach the surface. But this brings us back to the daytime paradox. If shorter wavelengths scatter more aggressively, blue shouldn't be the winner. Violet has an even shorter wavelength than blue, which means it undergoes the most extreme Rayleigh scattering of all. Based on atmospheric physics alone, the daytime sky is completely saturated with scattered violet light right now. If the atmosphere above us is essentially a giant violet radiator, the reason we don't see it isn't in the sky, it's in our own biology. To fully resolve this daytime paradox, we have to look closely at the biological hardware receiving that light. This chart shows the sun's actual energy output across the color spectrum. Our star produces slightly less violet light than blue to begin with, but that minor dip isn't enough to explain why the violet light disappears. The reason we see blue lies in the anatomy of the retina, specifically the cone cells and a biological pigment called melanopsin. Melanopsin is the primary receptor for shorter wavelengths. It makes our eyes highly sensitive to blue light, but as those wavelengths tighten toward violet, our visual sensitivity drops off. Humans are simply not very good at detecting violet light. When the mixture of light from the sky enters the eye, our neural pathways prioritize the blue signal. Even though the atmosphere is full of scattered violet light, our visual system emphasizes the blue wavelengths, rendering the sky as the shade we recognize. We see a blue sky because our biology acts as a filter for the raw data of the universe. The color of the sky is a product of cosmic mechanics meeting the specific biological constraints of the human eye.